Is it a good idea to build an entire computer from scratch on breadboards like this? Well, it might seem like a strange question from someone who's basically made an entire YouTube channel out of doing precisely that. And I sell kits with all the parts so you can do it yourself. So obviously I'm a pretty big fan of building computers on breadboards. And the big reason I really like it is that it forces you to think through how everything works. It always felt like something was missing with these projects where you get a pre-made circuit board and you just solder a bunch of components to it. And don't get me wrong, it's great if you want to learn how to solder, but once you know that, I just don't see how attaching a bunch of components to a circuit board teaches you much about electronics. In fact, the typical experience is that you solder the whole thing together, plug it in, and it just works the first time. There's nothing to troubleshoot. There's no need to understand how it works, and so you don't. This, on the other hand, it really forces you to think about each individual connection to each pin, and as you build each section, testing it, each as you go, there's a very good chance things aren't going to work perfectly the first time, and that's a good thing. It forces you to think about why, and it helps you build a deeper intuition for how it all works. And so that's what I really like about doing big projects like this on breadboards. But aside from being a lot more work, which I think is a good thing, there are definitely some caveats to be aware of when building complex projects like this on breadboards. First, not all breadboards are the same. There's a big difference in quality between the cheap $2 breadboards you can get and a higher quality, $8 or $9 breadboard. And it's true, they look pretty similar, but let's take a look inside. Each row on the breadboard is connected with a metal strip that grabs the wires that are inserted. And if I dig under the backing here, I can remove that metal piece so we can take a closer look at it. And here it is. This is what it looks like. If we take a closer look, you can see the wires are inserted like this here and make contact with the metal here. And in a good quality breadboard, this metal is nice and flexible. And you can see even if you insert the wire at kind of a weird angle like this, it flexes like that and then pops back nicely. You can also see it's nicely shaped so that when you insert the wire from the top, which is what you'd be doing, it kind of finds its way in there nicely. So these make very good contact with the wire, spring back so they last a long time and everything else. Now let's take a look at the cheaper breadboards. Now, the construction on the cheaper breadboard is pretty much the same, so it's actually pretty hard to tell the quality just by looking at a breadboard, which is unfortunate because it means it's easy to pay for a high-quality breadboard and end up receiving one that's lower quality. And it may not even be the fault of the person selling it to you, since they may just not realize that there's such a big difference. But anyway, here's the same piece from the cheap breadboard, so let's take a look at the difference. And so you can see it's the same basic shape, but right away you can see there's a huge difference here. The metal's just not as springy, and so it doesn't snap back together, and so it may not make great contact with the wire, as you can see here. And it actually gets worse, over time. If you, insert something big, you can actually bend this out of shape. And I mean, that's maybe a little bit extreme for what you might stick into a breadboard. But once that's bent out of shape, nothing, you're not going to make great contact there. And so the quality of this breadboard and the quality of the connections you're going to get is much worse. So there's a big quality difference, and you can even see the, just the shape of the top there where the wire goes in is very different and much less consistent on the lower quality one. So the quality of the breadboard matters. You can run into a lot of problems building a more complex project like a computer on these cheaper breadboards because you just can't be as sure that all the wires are making good contact. And you can check out my website for more information on what breadboards I recommend. And of course, if you get any of my kits, they're all going to come with these high quality breadboards. But okay, even with the best breadboards, there's still a lot of limitations to building a complex design like a computer on breadboards versus a custom printed circuit board, or even these, soldered prototyping boards. And that's because the physical properties of the conductors in a circuit, whether that's the traces on a printed circuit board or the wires and breadboards in something like this, those conductors and everything have physical properties that affect the circuit. For example, it's easy to look at two wires like this, let's say these two wires here, and think, well, okay, this wire connects this point here to this point here, this wire connects this point here to this point up here, and maybe they don't really have anything to do with each other. And that's not entirely true. Anytime you have two pieces of metal close together, like you have these two wires that are close together maybe, you actually have a capacitor. And that's why the schematic symbol for a capacitor is two plates next to each other, but not touching. And the way a capacitor works is you have a difference in electrical potential on either side, and a charge builds up between these two plates. And another way of saying that you have a difference in electrical potential between 2 points is saying that you have a voltage across those points. That's what a voltage is. It's always, sort of a voltage measured between 2 points. and it's just the difference in electrical potential between those points. But with a capacitor in here, if you try to change that voltage, the capacitor will actually try to prevent that. So if you try to increase the voltage by adding more charge to one side, the capacitor is actually going to absorb that charge and charge up a bit before the voltage between these points actually changes. And then if you try to decrease the voltage here by pulling some of that charge away, the capacitor will discharge as much as it can to keep the voltage from dropping. And sometimes you want that. So for example, on the power rails, you actually don't want the voltage to fluctuate, right? We have 5 volts coming in, and we want 5 volts everywhere on our power rails to be actually 5 volts. We don't want it dropping and things like that. So if a chip is switching a circuit on and off and it has to draw more current to do that, we don't want the voltage on that power rail to drop. And so it's actually a good practice to add some capacitors just across the power rail like this. So I'll actually add a couple of 0.1 microfarad capacitors here across the power rails to help stabilize the 5 volts that are on those power rails. And really the best practice here is to have one of these capacitors for every chip that's in your circuit. So for example, we could have a capacitor here directly from 5 volts to ground across this power rail for this chip here, like this. And so that means that if this chip has any change in the amount of current it needs to draw from its power rails, it's always going to see a consistent 5 volts or as close as we can get to that. And so the closer you can put the capacitor to the power inputs for any particular chip, the better stabilized the power is going to be for that chip. And that's, I guess, one of the other maybe drawbacks of breadboards is that it's kind of hard or at least inconvenient to get these capacitors directly across the power rails of a chip like this. You've got to kind of put it across, and some of these chips, the powers is just kind of in an inconvenient place. But I think, for what we're doing, it's probably good enough just to have a couple capacitors here. These will still help stabilize the power rails without, really getting in the way too much. So that's fine. We can add capacitors here if we want to stabilize the voltage and keep the voltage from changing like we do on our power rails. But elsewhere, we have signals that need to change voltage rapidly. Any of these signals needs to change voltage rapidly because they're, carrying signals and that has to change. And so the stray capacitance that inherently exists in a breadboard or even a printed circuit board can cause problems. And since one factor that determines how much charge a capacitor can hold is actually the physical area of the conductive plates in that capacitor, you're more likely to have a lot more capacitance in a breadboard circuit just because you've got a lot more metal in here, in the breadboard and in all these wires than you might have in other types of circuits. Now, another related phenomenon is inductance. And if you've learned a little bit of physics, you might know that anytime you have a current flowing through a wire like this, there's a magnetic field that is generated around that wire. Of course, if you have a lot of wire, especially wound up like this, you can use that magnetic field to do work. And that's how a motor works. And that actually works in reverse as well. So right now I'm using current to generate a magnetic field that's pushing against this fixed magnet here. But any motor is also a generator, and that's because a changing magnetic field around a wire will induce a voltage in the wire. So when I spin this, the magnetic field from the permanent magnet changes relative to the wire and induces a voltage in the wire. So what does this mean for a breadboard computer? Well, if you've got a wire with a current going through it, you're going to have a magnetic field around that wire. And if the current flowing through the wire changes, then the magnetic field is going to change. So if we go from a smaller current to a larger current, we're going to go from a smaller magnetic field to a larger magnetic field. But remember, if you have a changing magnetic field around a wire, then the voltage, that'll induce a voltage in the wire. And it just so happens that the voltage that's induced will oppose the change in current. And so you've got capacitance, which opposes a change in voltage, and inductance, which opposes a change in current. And both effects are relatively small, unless that voltage or current is changing very rapidly. Well, how rapidly? If we take the 6502 computer that we're building, I've said that I plan to run this at 1 megahertz. So are we going to have any issues with 1 megahertz signals? So that's potentially alternating between 0 and 5 volts a million times per second. Is that going to be a problem? Well, we can run a little experiment. I've got a breadboard here with a bunch of connections, and I can feed a signal in on one side, and you can see I'm measuring that signal as well. If we look on the oscilloscope, you can see there's this 100 kilohertz sine wave that we're measuring going in. And so that goes in on this side, and then it goes through a whole bunch of connections, and then we can measure it coming out over here. Now, I also have a resistor here to kind of isolate the input and output measurements. And aside from that induced current that we're going to be looking at that I mentioned, I don't expect any current flowing through that resistor. So Ohm's law says no current flowing through it means no change in voltage, so we should measure the same voltage going in here and coming out over here. So here's the signal going in. It's a 1 kilohertz sine wave, and we're measuring that over on the left here, but we can also measure the output on the right. And so if I overlay that, you can see it's pretty much the same thing. And that's not too much of a surprise since we basically just have a wire going through the breadboard. But if we increase the frequency, I can dial this up. So that was 100 kilohertz. So if we keep going up, we can go to 1 megahertz, zoom in here, and it still looks like pretty much the same signal going in and out. But if we keep going, higher and higher frequencies, zoom in here, you actually start to see something happening here. You see the output, which is the yellow. Actually, no, the yellow is the input. So you see the green, which is the output, is actually shifting a little bit from the yellow. So there's a phase shift happening there, which is kind of interesting. And that is perhaps because that inductance and capacitance that I talked about is going to resist a change in voltage, is going to resist a change in current. And so it may delay and actually cause that phase shift. So we're starting to see that. And if we go higher and higher frequencies, you'll see not only does the phase shift increase, but you also see the green, which is the output, is actually decreasing. So it's starting to attenuate. And so if we go higher and higher frequencies, and that's about as high as we can go, up to 20 megahertz is as high as I can go with this. But you can start to see that the green signal, which is our output, is being attenuated. It's being phase shifted and it's being attenuated. And actually what I can do is I can automatically sweep through all of the frequencies here. So I'll do a, let's see, frequency response analysis and run analysis. And what this will do is actually sweep through all the frequencies from 100 hertz all the way up to 20 megahertz, which is as fast as this will go. And what you're seeing is it's plotting the phase shift, which is, I believe, the red line. So you can see that's staying pretty close to 0. And then it's also plotting the gain, or in our case, attenuation, which is the blue line. And that's also staying pretty close to 0. And here we are at 100 kilohertz, and it's still pretty close to 0. As we approach 1 megahertz, you see the phase shift is starting to change. And that's what we saw when we were looking at it ourselves. And then as we get, looks kind of 5 megahertz or beyond, we're starting to see the blue line is also dipping by a few decibels. And so that's showing that at higher and higher frequencies, we're starting to lose some of our signal integrity. Something else is kind of interesting. If we go back and just look at the waveforms here, remember that the attenuation and phase shift that we're seeing is a result of both capacitance between conductors here, as well as inductance, which is actually a magnetic field that's generated around these conductors. So if we actually change sort of the physical shape here, or properties, or sort of relationships between the different wires, you can see just as I poke at this, that the phase shift and the attenuation that we're seeing is changing a bit as well. And this is at 20 megahertz, but I don't know. I think that's pretty interesting to see that. So you can see at higher frequencies we are starting to see some signal integrity issues. But we want to run our computer at 1 megahertz here, and 1 megahertz looks like no problem, right? We're still 0 attenuation. Our phase shift here hasn't shifted by very much at all at 1 megahertz. And even the attenuation that we do see is exaggerated quite a bit because of that resistor I added to make this more of a worst case demonstration. So even in this pretty messy scenario that we've got here, things look pretty clean up to 1 megahertz. So we ought to be fine, right? Well, it's not so simple. The clock for the computer is 1 megahertz, but it's not a sine wave like we've been looking at. It's a square wave. It just toggles from 0 to 5 volts. But in reality, any signal, including a square wave, is actually made up of sine waves. So here's a 1 megahertz sine wave, and I'm generating it with this first formula here, which has a frequency of 1 million. And so you can see the period here is 1 times 10 to the minus 6th, or 1 microsecond. So that's 1 megahertz. But of course, it's a sine wave, and we're looking for a square wave. Well, we can get closer to a square wave by adding another sine wave to it. So here is a 3 megahertz sine wave, and I've made it 1/3 of the amplitude. And if I add these two together, so f of x and g of x, if I add those together, we get this, which is a little bit more square-shaped. But if I add to that h of x, which is a 5 megahertz square wave at 1/5 the amplitude, so if we add h of x, you can see it gets a little more square-shaped. And we can keep going. I can add this next sine wave, which is 7 megahertz. And you can see it gets even more square-shaped. The slopes are a little bit steeper here. The tops are a little bit flatter. And in fact, to get a true square wave, we could add up all of the odd-numbered multiples of the fundamental frequency, which in this case is 1 megahertz, And if we add all of those up all the way to infinity, that would give us a true square wave. So let's take a look at this other setup here that I've got. So I've actually got a formula here that represents the sum of odd numbered multiples of a 1 megahertz sine wave. And I've got this 2k minus 1 factor in here, as well as dividing by 2k minus 1. So if k goes 1, 2, 3, 4, 5, then 2k minus 1 is going to go 1, 3, 5, 7, 9. So that gets all of the odd multiples. And then we're summing up all of those for k going from 1 all the way up to n, which right now n is also 1. So right now we're only getting the first term, which is why we just see that 1 megahertz sine wave. Then I've got some other stuff in here just to kind of scale this up, and we're adding 2.5 here, just so that this wave overall goes from around 0 at the bottom to sort of around 5 at the top, just to kind of give us something like that 0 to 5 volt square wave that we're looking for. But now this makes it easy for us to add more terms, because I can just change that n. And so this is where we were before with n equal to 4, with 4 terms. But we can keep going, and the more terms that I add, the more and more it looks like a square wave. But also, the more terms that we add, the more the higher the frequency. So this looks like a nice sharp square wave, but the frequency, the maximum frequency that I'm using to get that is over 100 megahertz. So, in reality, because high frequencies like 115 megahertz are going to be very susceptible to small amounts of capacitance and small amounts of inductance, like we've got in a breadboard circuit, we're definitely not going to see perfect square waves with perfectly steep slopes like this or anything like that in real life. So the question is that a big deal? Well, in my last video, we looked at this timing diagram for the 6502 CPU, and we figured out that we weren't going to have any problems complying with all of the constraints that are set out in here. But there's one actual timing requirement that I kind of glossed over that actually turns out to be one of the hardest constraints to meet. And that's, this time here, this TF, which is the fall time, and TR, which is the rise time of the clock. So what is that requirement, fall time and rise time? Well, we flip over here. We can see fall time, rise time is a maximum of 5 nanoseconds. 5 nanoseconds is not a lot of time. And just to get a picture of that, I can add 2 lines here that are 5 nanoseconds apart. So I'll add these two, and these are centered around 5 times 10 to the minus 7th, which is half a microsecond. So it's centered around this point, sort of halfway through, which is where we have this transition. And then it's bracketed, plus or minus 2.5 nanoseconds, basically 10 to the minus 9. So, minus 2.5 to plus 2.5 is going to give us a gap here between these 2 lines of 5 nanoseconds. And so as you can see, 5 nanoseconds is really short. So let me zoom in here and see if we can see what's going on a little bit better. So I'll change the x-axis to go from 4 times 10 to the minus 7 to 6 times 10 to the minus 7. So there we can see things a little bit better. And you can see we're going from 5 volts down to 0 volts within that 5 nanosecond window. But remember, for this signal to exist that we're graphing here, this red signal, there must be a component of it that's 115 megahertz. Yeah, so if we don't think our breadboard circuit's going to handle a 115 megahertz signal all that well, then we shouldn't expect to see a square wave with slopes quite this steep. So if we go down to let's say where our maximum frequency is closer to maybe 30 megahertz, you can see here even in theory, we definitely can't transition from 5 volts down to 0 volts within this 5 nanosecond window. But, one piece of good news is that we don't actually have to get all the way from 5 volts down to 0 volts in that time frame. We just have to get from high to low. And it turns out that high is really anything above about 3.5 volts, and low is anything below about 1.5 volts. So really, something like this would be in spec, right? Because we're going from the absolute minimum of what's considered high to the absolute maximum of what's considered low. We're doing that within that 5 nanosecond window. So this would technically be in spec. And so maybe that maximum frequency is really something more like, I don't know, it's hard to see, but maybe it's like 43, 45 megahertz. And of course, this is just a model that shows all of the frequencies up to 45 megahertz and then none of the frequencies above that. In real life, we'd still have all of the frequencies. It's just that as we get higher, they become more and more attenuated, not to mention phase shifted, as we saw. But the point is that the model, isn't perfect here, but hopefully gives you just some sort of idea of what's going on. The other reality is that this 555 timer clock module that I've been using is not exactly great at meeting that 5 nanosecond requirement either. And it's been working fine. If we take a look at it, you can see, this is 5 nanoseconds per division. So, going from, let's say it's 1.5 volts here up to the 3.5 volts, which is actually about as high as it gets, is a little bit more than 5 nanoseconds. So, it's not technically in spec, but it's been working fine. So for, an educational or hobby project like this, particularly if we aren't running close to the 14 megahertz limit of the processor, or we aren't at any temperature extremes or anything like that, there's plenty of tolerance, and close enough is probably good enough. But let's hook up this 1 megahertz oscillator and measure it and see how close we really are. Now I've run out of room, so I'll need to add another breadboard here. And I'll connect the power rails and add the oscillator here. And the oscillator is pretty straightforward. We just connect power and ground to it. So power goes here to the sort of top left pin, ground to the bottom right pin over here. And that powers it up. And then this top right pin, we're just going to get a 1 megahertz square wave coming out of that. So let me hook up the power here and we can take a look at that. Obviously the computer's not going to do anything because we have no clock connected to it now. But let's measure the output of our oscillator. So with the oscilloscope probe here, rather than using the ground lead, the best way to measure this, because the ground lead, this is a wire, it's got inductance in it, it's going to have all the same problems that all these other wires have. So to get the best measurement, you want to get rid of this. You also want to get rid of the clip, and you just want to use the probe, and then actually this little ring here is also ground. So you can use this little ground thing, stick that on there like that, and then you've got a ground and then the probe. So I'll put the probe here on the output that we want to measure, and then the ground thing is just going to connect, or sort of be stuck to the case here, and that's going to be ground because the case is grounded. So that's the best way to get a really accurate measurement of what's coming directly out of the oscillator here. And if we take a look at that, we can see we've got a 1 megahertz square wave here. And if we zoom in a little bit, you can see there is a little bit of overshoot and a little bit of ringing there, kind of like we expected. But overall, it's a pretty sharp edge. So let's zoom in here to, so this is now 5 nanoseconds per division. So between these vertical lines here, these vertical grid lines, is 5 nanoseconds. So you can see the actual rise time is much less than 5 nanoseconds for the whole thing. Let me kind of shift things over here. So let's say our rise is starting right there. We're already up to 5 volts within about 2.5, maybe 3 nanoseconds. So measuring what's coming directly out of the oscillator like this, we've got a really great signal. But of course, we're kind of avoiding as much of the breadboard as possible, but with this measurement technique. In reality, by the time our signal gets to our processor, it might be degraded a little bit. But let's take a look at that. Let's do that. So what I'll do is I'll connect the clock into the rest of our clock signal from the rest of our computer. So that's there, and we'll connect that down to our clock there. And so you can see we're taking the output of the clock, and it's going directly into both the interface adapter as well as up to the CPU here. And so the question is going to be, what does our clock look like as it's going into the CPU here? So we can do the same thing. I can get this little ground probe into our ground, and then get our regular probe into that part of the breadboard, and that'll measure the clock signal up here. And if you notice, it's really not that bad. Again, this is 5 nanosecond per division here, so we're getting, all the way from 0 volts up to 5 volts in, maybe it's taken a little bit more time. Maybe this slope's not quite as steep. Perhaps I'll edit this video to overlay the two of these so you can really compare. But at least to my eye, looking at this, just my memory of what the other one looked like, it looks like the slope is a little bit less steep, but not terribly so. And this is actually really encouraging because you remember that when we were looking, theoretically at just doing the math, we needed, 100 megahertz plus signals to get from 0 volts to 5 volts within 5 nanoseconds. So this is very steep. So we must actually be able to maintain those really high frequency, or at least enough of those really high frequency signals to be able to get something like this. So this is very encouraging. Though, of course, I've done everything I can to get the best possible case here. Obviously I'm using high quality breadboards. These wires are as short as they could possibly be. and they route as directly as I could make them route. And I think that is important for the clock circuit here. So if, some of these other signals, maybe, you can have longer wires or whatever, but the clock signal is one where, because the datasheet has that spec of 5 nanosecond rise time, 5 nanosecond fall time, in order to meet that spec, it seems like it's worth, going to a little bit of extra effort to make those connections nice and neat and as short as they need to be. So everything looks good. We're running a clock at 1 megahertz. So let's reset. And it looks like there is still one problem, which is that our program to display Hello World doesn't actually seem to be working anymore. So if we reset, we could try to disconnect, reconnect power, but it's just not working. Though it is sort of doing something. So let me actually disconnect and reconnect power. I'll disconnect this, reconnect it. And you can see the LCD comes up and it's not initialized. But if we reset the computer so the Hello World program runs, you can see the LCD does appear to initialize. It gets set to 2-line mode, the cursor shows up, but it doesn't do anything else. So it looks like there still might be some sort of problem running the computer at this higher speed of 1 megahertz. So what's going on? Well, there's something I remember seeing in the datasheet for the LCD controller, a while ago when we first hooked it up. And that is that there are several places in the datasheet where it says you have to be sure that it's not in the busy state before sending an instruction, right? When an instruction is being executed, no instruction other than a busy flag read instruction can be executed. The busy flag is set to 1 when an instruction is being executed. Check it to make sure it's 0 before sending in another instruction. Be sure it's not in the busy state before sending instruction. And at the time we first hooked the LCD module up, I kind of glossed over this because we're running the clock so slowly that there was basically no chance that the LCD would still be executing one instruction by the time we sent it the next instruction. In fact, I don't even know if I mentioned it at the time, but I do remember seeing this in the datasheet and making a mental note that I could probably ignore it while we were running the clock really slowly, but that eventually I'd need to come back and actually add the code to read the busy flag and wait before sending each instruction or character to the LCD module. But now that we've got a good clock signal, it looks like everything else is working because the LCD is being initialized, and the first instruction sent to the LCD is the one that initializes it and sets it to 2-line display mode. It puts it in this state. It's just that all the rest of the instructions are probably coming too quickly before it's ready for any of them. So these instructions, turning the display on, cursor on, clearing the display, these probably aren't actually working, even though the cursor is on and the display is cleared. It's just that those are the defaults when the LCD first powers on anyway. And then, of course, these commands where it actually prints each character aren't working either. All of these instructions are being sent so quickly that the LCD isn't actually done executing the first instruction before the rest of them are sent. And that's because we don't have any code to check for that busy flag and wait to send the next instruction when the LCD is ready. And at 1 megahertz, it's just going too fast for the LCD. So since we've got a good clock signal, I think all we need to do is just add the check for the busy flag, and we can do that entirely in software. And that's what I'm going to do in the next video. And remember, if you want to follow along with these videos, you can get all the parts I'm using over at my website, eater.net/6502. And for now, at least, we're still able to ship kits during the ongoing coronavirus pandemic. And I'll keep my website up to date if that changes. But, if you're stuck inside looking for something to do, got you covered.